Welcome back to another episode of Quintessence. In this episode, we're going to be completely restarting the game, this time making it in C++, but we'll still have a web port. I did this for many reasons, which I won't get into in this video. The main one being that JavaScript isn't made for making large-scale games, and hopefully every week on Friday I can get a new update out and a new video covering what I did. With that being said, we can get straight into it and start working on the main screen. Here we have some basic C++ code with a couple of just little libraries I made, as well as some imported like stb image. And this is our main CCP file where everything starts that has an include header file that just has a function that sets up glfw returning a window. But to keep this main file clean, we're going to make a new folder called main screen, and we're going to create this folder in both the source file and header file. In the header file, we're going to make a class called main screen. The first thing we're going to do is define the UI renderer. So we're going to include the UI renderer that I made here. We're going to make a private variable called UI renderer, which is an instance of the UI renderer class. Now we can move to defining these in the CPP file. Now we can define the UI renderer, which is just going to be a new UI renderer. It takes in one argument of window, which we currently don't have access to in this scope, but we do in the main file. Because our main screen class is going to be created here in the main file, in the constructor we can just take in a window, which can now be passed into the UI renderer. Now we need to run a few setup functions on the renderer. One of them being setRatio, which sets the ratio of how much of the screen to be used for rendering UI. It's set up this way so no matter what resolution of screen you're using, the UI will always still be proportional. For now, the ratio is going to be 16:9. We also have another function called setRatioScale, which pretty much just sets the actual units that the UI will use when being defined. So if we set something like 100, the UI renderer's screen size will be 1600 by 900. This has nothing to do with the resolution of the screen you're using. Having the UI space be something like 1600 is just a lot easier than if the UI space was like from 0 to 16 or from 0 to 1. I hope that made sense. Now we need to move on to giving the UI renderer access to some controls. To do this, we're going to go back to our render header file, define a static function called resize window callback. This will be the callback function that is ran by OpenGL when the window is resized, and it needs to be static for it to work. Next, we need the callback for mouse move, so we're just going to call it mouse move callback. Next is mouse button callback. Now we need to define variables so that when these callbacks are called, we can set a new value to them. We're going to have a variable called window width. We're going to set to 0 by default. Same with window height. We're going to have two more. One called mouse X, another called mouse Y. Next, we're going to make two booleans. One called mouse button down, set to false by default. This variable is going to be when the mouse key is actually down. And we're going to have a variable called mouse down. This is when the game will think the mouse is down. For example, if you were to click on something like a button, it would set mouse down to false because the button's been clicked on, but the actual mouse button still could be down, so this would still be true. With all these defined, we can move back to here and set them to the new values. And that's it for these callbacks. Now we need to give the renderer pointers to the variables that we just made so we can know the actions as well. Now we've given the UI renderer access to all these inputs. That's pretty much the setup of the UI renderer done. Now that all the code for the callbacks are done, we just need to tell OpenGL which callback is which, and we can do that using this function I made, which takes in an instance of a struct. This struct pretty much just contains a bunch of different callbacks, and then this function gives OpenGL each of these three callbacks. And then we're going to use our resize window function just to set the window to a default value. But currently this will just immediately close after being created because we have no loop. So let's make two functions for the main screen, one of them being the function that draws main screen, and one of them being the function that updates the main screen. And update loop returns a boolean on whether or not to keep running the loop. So if it returns true, the loop will continue, and if it returns false, the loop will stop. And with these few lines of code, that checks OpenGL if any events have happened. Then we return false ending the loop if OpenGL detects that the window has been closed. But if the window didn't close, it'll return true, continuing the loop. And for now, that's all the code we really need for the update loop. So here in our draw loop, we need some code to clear the screen and fill it to black. We also need this glfw function, That takes what GLFW is rendered and makes it visible on the screen. Now that we have two functions for drawing and updating main screen, we need to put them into a loop. And then here at the end of our constructor, we can define a loop. And for the code of the loop, I'm just going to use this little loop library I made, which is just a single loop class that takes in a draw loop and update loop. We'll make a new loop called main loop. To run start loop, we're going to need to pass in the number of times a second we want the update loop to run, which for now is going to be 45. And then we pass in the update function. The next argument is going to be the target FPS, which will be 60. And then we pass the draw function. So now for actually rendering the UI, in the draw loop, we're going to create a new button, calling this button starter button. This button has a few properties, one of these values being sprite name, which is set to starter button. But the starter button sprite hasn't been initialized yet in the UI renderer. So we're going to go to the constructor. And to give the UI renderer the start button sprite, we first need to set the size of the texture's atlas, which for now we're just going to set to the size of the restart button. Because for the UI renderer, we're only going to need space for one sprite. And we're going to draw the start button on the atlas at 0, 0, and give it the sprite named start button. This needs to go before the loop or it'll never get executed. Now we need to draw the UI to the screen, and we can do that by running render UI on our UI renderer, passing in our start button. And then we can tell the UI renderer to draw all of the UI elements to the screen. Never test it, we should hopefully see our start button. And this now works, it's just very stretched. So we're gonna make the button a little bit bigger. And to fix the stretching, we're just gonna set its width to 500 and set the height to 500 times the ratio of its width to its height. This makes it render proportionally. Now we just need to center it on the screen. Now that it's centered, I think it looks pretty good. Now it's just time to add the background. This panorama is going to be split up into two parts that will match so that it can appear to scroll infinitely. Now to render the background, we're going to create a new render. Give it a vertex and fragment shader for rendering images on the screen. We're going to give it the same window ratio as the UI renderer, so things will always be in the same place. And then do a lot of the same setup that we did for our UI renderer. We're going to create two sprites of our two parts of our panorama. And then when the window is resized, resize how much space our background renderer will take up. Finally, all we need to do is to render the background before we render the UI. And it now looks like this, which I think is pretty good. Now we just need to make it so the panorama scrolls. And to add the scrolling functionality, we just need to add another sprite, which is the second part of the panorama. And then here, we're adding these three objects, the background renderer. Each one of these objects is one of these panorama images. How this will work is we're going to put all the panorama images next to each other, and then have a panorama offset uniform. And this panorama offset in the shader just shifts all of the panorama images left. And then we have an if statement, checking if the offset has reached the third panorama image. And if it does, it just sets the offset back to the start. This works if we only have two panorama images, and the first and third one are the same. So it appears like it seamlessly loops. And if we test it, it looks like this, which I think looks pretty good. There is a slight problem. That being when it loops back to the start, you could see where the image ended and how it looped back. And you see that because the renderer is going off the screen space as if every monitor was perfectly a 16:9 ratio. Because this ratio is just slightly off 16:9, we can see stuff that should be off screen, so we need to add borders to the screen. So then everything that's off screen is just black. And here we just have one final renderer. And all the fragment shader does is sets every pixel to be black. And then now there's no more funkiness on the side of the screen, because everything out of the bounds of the UI renderer is just covered up, because it should be off screen. I also added the star, which is going to be one of the main icons for the game. I also want to add a little bit of animation to the star, and a hover effect on the button, just so the starting screen feels a bit more interesting and less static. For the animation of the star, we're just going to have a star animation timer. And pretty much based on the star animation time variable, we just change the position of the Y of the star. That goes up until a certain point, and then the direction of the timer changes, and then the timer goes down. So now it pretty much repeatedly just hovers up and down. There's no animation to it, but it's just if the start button's being hovered over, it sets the size slightly higher. And when it's not hovered over, it sets the size back. It's definitely a much better way of doing this, but for now this works. The final product of the starting screen I think it looks pretty good. The star kind of slowly floats down and floats back up, and this just repeats infinitely. And when you go over the button, it grows slightly, and when you get off the button, it goes back normal. Okay, so now that the main screen is all done and dusted, we can move on to working on the game. We're going to start by adding two new folders, one in source files, one in header files. That'll include all our files for game. We can make a class called game. In this game class, we'll do a lot of the basic setup like we did for the starting screen. In the constructor, we're going to initialize the renderer. This render is very different than the one I made before for rendering the UI, which are two completely different classes. This one being focused on rendering anything. The renderer takes in both a fragment and vertex shader, as well as paste two basic ones in here. To initialize the render, it needs a window so it knows where to draw. We can get access to the window the same way we did with the starting screen by passing in the window into the constructor of the class. After main screen has been closed, we can create the game variable and pass in the window. And now we can pass this window into the renderer. But before we do any more work with the renderer, let's organize this code a bit by moving these into their own separate text files. So in resources, we're going to make a new folder called game with another folder in it called shaders. Now we can copy over the fragment shader and put it into fragmentshader.txt. Now we need to import these two text files. To do that, we're going to go to game.h, then make a new private function called readFile. So yeah, so this pretty much loops through every line, adds a new line character, and then adds it to data. And at the end of the function, we can just return data. Now back in the game's constructor, we can just run this read file with the file names of where both our fragment and vertex shaders are. This is pretty much the same thing, just a lot cleaner. Just like the UI render, the renderer needs some setup functions as well. We'll start with set window ratio, which will again do 16 by 9. This is very different than how the UI renderer set ratio was. Give the dimensions of a rectangle with this ratio that we can use to position anything we draw. It pretty much sets these four variables so that everything we draw on the screen is proportional. In the future, I do want to change this for the actual game, because for an actual game, you want the game to take up the entirety of the screen, not just a section of it. For simplicity's sake, we'll use this for now. Next is a function called set vertices per ID, which for this to make sense, I need to explain how I made my renderer work. Pretty much it works by I can call create object that returns an ID. Then we can use that ID to edit that created object later. Because this renderer is going to be responsible for rendering all the blocks, that will be all squares. We're going to do 6, because every triangle has 3 vertices, and we can make a square with 2 triangles. I'm going to change the name of the renderer to be a bit more clear. I'm just going to change it to block renderer. Next, we're going to set the vertex array to a new vertex array. The job of the vertex array is pretty much to tell OpenGL what the data we're giving it means and how many different values there's going to be for every vertex of a triangle, and more importantly, what all that data means. So on this vertex array, we're going to create a vertex buffer and set to a new vertex buffer. And pretty much a vertex array tells OpenGL what all of the data in the vertex buffer means. We're going to set texture to a new texture. The point of this texture class is for when we eventually work with images. We can send the images into the texture, bind it to a texture slot, and then OpenGL can render them on triangles. Now we need to set up the vertex array. On the vertex array, we're going to run push attrib, which takes in the vertex buffer we're using, the index size, which is 2, the type, which is GL float, and whether or not it to normalize the data we give it. We'll do false. Say for example, in this vertex buffer, we had this data. It's saying that attribute 0 has a size of 2 indices, these two. Data type float. Say for example, in this vertex buffer, we had this data, these being 3 positions of a triangle. Running push attribute says that each of these triangles' vertexes have 2 floats. That'll be the position where they're drawn. Because this is the first time we've run push attribute, this will be attribute 0. And if we go to the vertex shader, we can see attribute 0 is the position with a effect 2, meaning that it's 2 values, x and y. So now we can move on to rendering the blocks. Okay, so now in our update view function, which is a function that's ran when the window is resized, we're going to set the width and height of the block, and then with 2 for loops, we're just going to place as many blocks on screen that can fit. In the second for loop, we push 3 vertices, each having an x and y. So currently for test this, we'll have triangles going across the screen. To make these into full blocks, we just need to copy the code of these 3 vertices and change the vertice that was in the top left to be in the bottom right. Now as you can see, the entire screen is just completely white because each block is getting fully rendered, but currently it's kind of hard to see each individual block. So now in the block renderer, we're going to add a new attribute, this being color. That's going to be 4 bytes of RGBA. So now in a vertex shader, we need to take in this attribute and have a new variable called v_color, which will export this color to the fragment shader so it can correctly color the blocks. And then in our fragment shader, we can just take in this v_color and set color to the pixel v_color, which results in this, which looks really cool, but it's definitely not what we want. And then if we set each block to a random color, it'll look like this. Now we can set the texture class's atlas to the size of 2 blocks, and then render the PNGs of these 2 blocks onto the atlas. Now we want to switch the second attribute from being color to instead texture, which only needs 2 bytes of the X and Y location. What part of the atlas do you want to draw? And then now in our fragment and vertex shader, we just need to change where color used to be to reflect the changes we've now made. Now in our fragment shader, we take in a uniform sampler 2D, which is our texture, and then we use this texture combined with the varying texture chord to determine the pixel's color. We also need to change what data is being pushed to the vertex buffer. So now that all the blocks are being rendered on screen, we need to make the actual list of blocks in the world. We're going to do this by making a new array, which will be a vector of strings, and we're just going to call it blocks. Okay, so now in the constructor of the game, we can have 2 loops. And for now, we're going to hard code the size of the world to be 50 by 28. And here is where we're going to create every new block. And for now, we're just going to have every block in the world to be dirt. And now instead of setting these all to grass, we can set it to the corresponding block should be. We'll do this by making a string called block texture. Block texture should be the corresponding index of blocks. So now we can change all these to block texture. Now I just need to copy the 2 mouse callbacks from main screen, and we're also going to copy these 4 variables for the mouse position and left mouse state. I'm going to go to our game's main loop, and just to test if this mouse down works, we're going to set the block at index 0 to grass. Now hopefully if we run this and click, the block at the bottom left of the screen will be converted to dirt. Okay, so now if we click on the screen, nothing happens. The problem is, we're only refreshing the blocks when the screen detects that it's being resized. So if we resize a window, we can see that the block then updates. To fix this before every frame is rendered, we just need to check if any block states have been changed, and update them in OpenGL. We can fix this problem with block textures and updating by making a function that takes in a location that'll be pushed to a list. That list will be looped through before a new frame is rendered, and if there is any changes, it'll send it to OpenGL and update the texture. So we're first going to make an array of vec2, which we'll define as a struct with an x and a y. We're going to call the list potential texture updates, and we're going to call it update texture. And in the function, all we're going to do is push a location into the list of potential texture updates. And then here in our render loop, we can just loop through all these potential updates. Okay, so now it loops through all these potential updates, gets the block location, gets the current spread of that block, then gets the UV position of the texture on the atlas, and then these 4 texture coordinates are set to the 4 texture coordinates of each corner of the block. Now when we set the grass block, we can run update texture at location 0, 0. And if we run this, it should hopefully update. And now if we click, it immediately updates the texture. But every time we want to change a texture of a block, we don't want to have to run all this code. So we're going to abstract it all into a function called update block texture. And we can just copy this code from before and plug in the variables. This works exactly the same, it's just much cleaner. But we want the grass block to draw on the cursor, so we're going to make 2 new variables, int block mouse x and int block mouse y. And then on the move mouse callback, we can set them to these equations, which just gets the mouse's block position on the screen. So when I click, the block at our mouse's position will be set to grass. And now wherever I click on the screen turns to grass. Next, I want to add one more block to the game, that being air. So we'll expand the atlas and add the new texture. And now we're going to turn every block we click onto air to simulate breaking blocks. And if we test it, now as you can see, we can just break blocks. And now is probably a good time to address one of the biggest problems of the game from a technical standpoint, and also the world is a fixed size, and also that it's hard-coded. We're going to fix this by splitting the world into chunks, because that'll make dealing with stuff like rendering and multiplayer hopefully a lot easier. So we're going to go to game. We're going to change our blocks list to a map, change blocks to chunks with IDs of string, and make a unsigned int called chunk size, which for now we're going to set to 16. Now we're making a new function called generate chunk, and then give it the location of the chunk with a int x and y, and data of an array of every single block in the chunk. Like blocks, this is going to be a vector of string that represent the block ID. We're going to change blocks to chunks, and chunks should actually be a map with IDs of string, and a vector slash list, which will be the data of the chunk, which is a bunch of strings. In generate chunk now, we're going to create an array called blocks. This will be an array of strings. This list will have a size of chunk size times chunk size. Now we need two for loops. These for loops will loop through every block in the chunk and set it to something. And these two variables, block x and block y, which are the actual block locations, where the x and y in the for loops are just offsets from the chunk's start. Now we can just set blocks. This function right now pretty much loops through an empty chunk and fills all with dirt. Now that this blocks list is filled with dirt, we can set the chunk we want to generate to this list. The way I'm going to index chunks is by using strings, starting with the chunk x, then adding the string x to the back of it, and then adding chunk y. And this pretty much just gives every single chunk in the game a unique ID. Next, we need to change update block textures. We first need to specify what chunk we want to edit. We can do this by converting the location of the block to the chunk ID. We can do this by dividing the block x by chunk size, and then flooring it, which pretty much just means rounding it down. Adding the x between the x and the y, and then adding the y. Now we have this equation that just gets a chunk ID. Now we just need to get how offset this location is into the chunk, and this should now get how offset the block is into the chunk. Now to make the world, we can just run generate chunk at xy. This code should hopefully work, which it definitely didn't first try. And that's because as we're looping through the chunks, we're not actually accounting for the chunk's position. And currently the only way we can figure out where the chunk is by abstracting it from the chunk's name. But I think a much better solution to this is to make a new object for the chunk. This will have an array of strings. That'll be the ID for each block. This array will be called blocks. And then it's going to have an int x and y for the chunk x and y. And then now in the chunk map, its data will be a chunk instead of just the list of the IDs of blocks. Okay, so now when we're rendering a chunk, we now know x and y. We're first going to make these more specific and rename them to offset x and y. And then now this should prevent chunks from stacking on top of each other because it accounts for the chunks x and y. And then now test it. And now this works again, except for breaking blocks, which is very broken. So let's try and fix that. The first thing we're going to do is we're going to change how big each of our render's objects are to be one chunk, which is the number of blocks, which is chunk size times 4, because every block is 4 vertices. Now when we push objects to our block renderer, it needs to be the entire chunk instead of just a block. So we're going to move block up here, rename it to chunk vertices. 4 times 4 is a number of floats per block. So just like before, if we want to for the entire chunk, we just have to multiply it by chunk size squared. Make a new int called I, just for keeping track of where we are in the chunk. Replace all the blocks with these chunk vertices. And then we add I. I just realized I already had an int called I. So we're going to rename it to vertice index, which is a much better name anyway. At the end, we add 15 to vertice index. And at the very end, we just add the chunk. So now this loop should fill chunk vertices and then push it as an object. This is the result, so something's clearly very wrong. And the problem was this single number. This was 15 instead of 16. So now everything's back to normal. And we're going to add something to chunk. We're going to add an unsigned int called render object ID. And then here, once we have add object returns a object ID. So we'll set the chunk's object ID to the returned value of add objects. Now when we loop through potential texture updates, we'll edit the object, add the chunk's render object ID. We're going to also make a quick function called getChunk, which will take in an int for the x and the y and return a chunk. We can reuse most of this code, and we can quickly update this to make it a bit simpler. But finally, breaking blocks now works correctly again. I want to do a few more things just to make this even slightly playable. First of all, we're going to add a little bit of variation to when the world's generated. We're going to make it so if y equals, we'll say 7, then we'll set it to grass. And if y is less than 7, set to dirt. So if it's above 7, it'll be set to air. This will pretty much just make a flat plane you can build on. I must have messed up something somewhere because it's horizontal. The problem is actually multiplying the x instead of the y. And I need to check it against block y, which is the actual height of the block, instead of just y, which is the offset of the block in the chunk. And as you can see, we have a little world you can just kind of destroy blocks in. But I also want you to be able to place blocks. We can do that by pretty much copying what we do for breaking blocks. Make two new variables for right mouse button down. In the mouse button callback, we can just copy it and change mouse button 1 to mouse button 2, and mouse down to right mouse down. And then we can break this into its own if statement. So you first check this on the screen, then if left mouse down, it'll break blocks, and if right mouse down, it'll place blocks. For now, we'll set a place start. Now everything's working, you can both build and break blocks. Now it's just time to replace these with some better textures. I'm also going to change the color layer to make it more pale and make it more neutral and not so blue. This is currently the final game. As you can see, all the animations work. We can click play, and we can place blocks and destroy blocks. Everything has a nice texture and looks good. And that's all I planned for this video. And hopefully I'm not lazy, and by next week there'll be another update and another video covering what I did. With that being said, see you hopefully next week.